Hello and welcome to today's webcast, Using Propensity Scoring Analyses in Critical Care Research. Today's webcast is brought to you by Discovery, the Critical Care Research Network at SCCM. My name is Brandon Hobbs, Surgical Critical Care Clinical Pharmacist at Orlando Regional Medical Center in sunny Orlando, Florida. I will be moderating today's webcast, and I have no disclosures. This webcast is being recorded. The recording will be available to view on the SCCM YouTube channel within 5 business days. There is no CME associated with this educational program. However, there will be an evaluation sent at the conclusion. The link to that evaluation is also listed in the chat box for your convenience. You only need to complete it once at the end of this webcast. Your opinions and feedback are important to us as we plan and develop future educational offerings. Please take 5 to 10 minutes to complete the evaluation. Thank you all for joining us today. I just want to go over a few housekeeping items before we get started. There will be a Q&A session at the conclusion of the presentation. To submit questions throughout the presentation, type into the question box located on your control panel. We would like to thank the Clinical Pharmacy and Pharmacology section for their work coordinating the research webinar series. Our presenters today include Drs. Vincent Liu and Alejandro Schuler. Dr. Liu is a research scientist at the Kaiser Permanente Division of Research whose work focuses on leveraging EHR data and informatics for sepsis and acute care. He is also the Regional Director of Hospital Advanced Analytics and oversees the implementation of real-time predictive models across 21 hospitals in Kaiser Permanente, Northern California. Dr. Schuler is a data scientist at Kaiser Permanente Division of Research and collaborates with investigators from the Systems Research Initiative and is an expert on applying methods at the intersection of machine learning and causal inference to large-scale observational research using EHR data. Thank you for joining us, Drs. Liu and Schuler. Please take it away.
Great. Thank you so much. It's really a pleasure here for Alejandro and I to present about this topic of using propensity scores in critical care research. Sorry. So I think what we're going to cover over the course of this 40 minutes or so are these points. Looking at observational data that we have as an opportunity to drive new discovery. I'm going to take you to an example that was published in Critical Care Medicine relatively recently as a kind of a case study in using propensity scoring and looking at the impact of acute organ dysfunction on long-term outcomes in sepsis. Then Alejandro is going to dig into kind of the method and the rationale, why to use propensity scores and how to use them. Then I'll kind of take us back to the results that we found in our study as a case example of how this can help us gain insight into the questions that we have about sepsis and critical care. I'll spend a little bit of time talking about other examples in critical care and also pointing to, I think, some really high value resources through the Journal of Critical Care Medicine that folks can turn to when they're ready to apply some of these methods. So I think most people are familiar with this evidence hierarchy or evidence pyramid in which we grade the types of study designs according to their ability to really drive new practice change or to establish causality. And, at the base are things like expert opinion. We move through case series and case studies to case control studies. Really, we're going to be talking about the distinction between cohort studies. They can be done prospectively, but we're going to be talking about retrospective data and then randomized control trials. And then kind of finally, many have posited that meta-analyses of randomized trials or systematic reviews may be kind of the ultimate top of that evidence pyramid. I would suggest that actually applying results from randomized trials into real world practice and showing that they're efficacious is actually the height of this evidence pyramid. Now, why are we talking about using observational data? Because all around us, the capacity to unlock large-scale data is growing tremendously. And these two figures show not only a growth in the number of publications in which big data is noted here on top in blue, but also the cumulative number of publications which focus on data-intensive applications, whether those are bioinformatics, other types of health informatics, sensing, and also imaging. Much of that is being driven by near universal EHR adoption across the United States. And this figure of the states show the percent of all eligible hospitals that have demonstrated meaningful use or upgraded any EHR. And you can see that, our lowest numbers at 97% and our highest are at 100%. So driven by the HITECH Act, we've seen widespread deployment of EHR systems, which in many ways have become the central nervous system of healthcare delivery today, and thus a massive repository of data which is available within our health systems, within our hospitals and other care environments to use to drive new discovery. But we face some challenges. Currently, we are struggling both with too much evidence, an overwhelming number of publications and other research reports to keep up with, and too little evidence, because despite the massive number of publications we see, a large majority of our care is actually not evidence-based. So maybe for a patient who we're caring for in the hospital who gets 50 interventions over the course of their hospitalization, very, very few of them actually have a representative, for example, randomized trial that demonstrates the benefits of one approach versus the other. The other thing we struggle with is the tremendous time lag between the publication of strong evidence, for example, in randomized trial, and then implementation into routine care. And, different studies have estimated that time lag is about 17 years from the publication of that gold standard RCT evidence to actually dissemination broadly. And we see that in critical care in a number of things, perhaps most profoundly in low tidal volume or lung protective ventilation, despite the fact that ARDS-NET work was published in 2000, we still struggle with complying with elements of lung protective ventilation. And then following the results of randomized trials, those gold standard evidence-generating studies in critical care could both give us whiplash and bankruptcy. So, we've seen, recommendations for protocolized sepsis care being beneficial, and then away from protocolized sepsis care being beneficial, and for steroids, and away from steroids, and for most recently neuromuscular blockers, and then away from neurovascular blockers in severe hypoxemic respiratory failure. And each time these trials are done, they're also extremely expensive and really difficult to conduct. And so the ability to rapidly generate new evidence is challenged, and then that evidence is dynamically changing over time. So that leaves us with a question, which is there an opportunity, or what could be the opportunity to learn causal effects from the observational large-scale data which we're accumulating with each patient that's cared for within our modern hospital systems? And this was a question we actually wanted to apply to a specific clinical conundrum, and that was looking at organ dysfunction in sepsis and how acute organ dysfunction impacted longer-term outcomes. So everyone, I think, on this call is familiar with sepsis. It's defined as the life-threatening organ dysfunction caused by a dysregulated host response to infection. We know that sepsis exacts a considerable in-hospital toll in terms of morbidity and mortality. We also know that its effects last long after patients are discharged from the hospital, both in readmission rates, complications, and as well as mortality in the years following sepsis. What we don't know is the relationship between the different types of acute organ dysfunction and how they relate to long-term mortality. And the reason that this knowledge is valuable is because it could, one, help us understand how to prognosticate, that is to talk to our patients or to set up the right structures in order to identify high-risk patients based on the types of organ failure which they had during the hospitalization during sepsis, but also to ameliorate or mitigate the long-term impact of sepsis on survivors. So this was our conceptual model. We have an episode of sepsis, and we're looking at outcome here, which is long-term mortality up to 1 year following that episode of sepsis. You can conceptualize this as our exposure of 6 different types of organ failure, which are those which make up the SOFA score. So respiratory, coagulation, liver, cardiovascular, neurologic, and renal. And ultimately, we wanted to understand the impact of the exposure on the outcome, but we faced the problem, which is that pre-sepsis factors differentially influence the likelihood of each organ failing. Because of the fact that patients with underlying chronic kidney disease were much more likely to have acute kidney injury, we needed to account for the likelihood or the propensity that patients, based on their pre-sepsis factors, looking 1 year back in their medical history, what was the likelihood that that patient would actually experience the acute organ failure. And the same was true for neurologic disease. For example, patients with dementia or prior delirium, much more likely to have neurologic dysfunction acutely. Similarly for all of these, respiratory, liver, and cardiovascular. And so this became the question in which we decided to apply the propensity score approach. How do we identify the independent effect of each organ failure on long-term mortality while adjusting for the likelihood of each patient developing that specific type of organ failure? So that's a lot. I think I'm going to turn it over to Alejandro at this point to take us through kind of how and why we use a propensity score in this approach.
All right. Hello, everyone. I'm Alejandro, and I'm going to take you through, as Vinny said, a little bit about the basis for propensity scoring methodology and how it works, why to use it, when not to use it. And so we'll start at first with this, what's called the potential outcomes framework. And I also want to point out that for a lot of these slides down here at the bottom, I think you can see my mouse moving. I have a couple of citations, and hopefully these slides will be available after the presentation. And so that's where you can look to find more information about any of the material that I discussed. So in the potential outcomes framework, we envision that the data sits in a table like this, where we have a column that indicates the patient, and then some columns that indicate some pre-existing covariates for the patients, like their age, for instance. And then there's the exposure, which in this case, in this example, I'm saying is a surgery, and there's 2 surgeries, A and B. And then traditionally you would think of, well, one column indicating their months to recovery. Let's say that's the outcome. How long does it take patients to recover from each of these surgeries? And we're interested in finding out which surgery leads to faster recovery time. So typically you'd imagine that both of these months to recovery given A and given B would be one column, just months to recovery. But when you think about it in terms of potential outcomes, there really are 2 columns here. One is how long would it have taken if they had had surgery A, and the second is how long would it have taken if this person had been given surgery B. And the fundamental problem of causal inference is that there's missing data, because if you get surgery B, you will never see what would have happened to this patient if they had been given surgery A. And the treatment effect that you're actually interested in is the difference in the averages between these 2 columns. What is the average number of months to recovery given A versus the average number of months to recovery given B? So you start to see the problem, because if the populations that are given A and the population that is given B are different at baseline, then the missing numbers, that what I have here is the question marks, are going to be biased in a certain direction. So if, like, let's say the B population is older, then you're going to see a lot of longer months to recovery in the B column, just because those people are older. And the missing observations that you're not seeing in those columns are for the younger people, which would be smaller numbers. And so if you just take the difference of averages and you don't account for the fact that those populations are different, then you're going to get a biased result, which is not what the result, which is to say that the result you would have gotten had you observed those missing potential outcomes. And so that's called confounding. That's the basic problem of observational research, of causal inference. And as some of you may know, if you randomize the treatment, you give A and B surgeries to the population by a coin flip. The reason that works is because then you have two populations that are identical on average, and then you can ignore those question marks, those unknowns, because on average they're not going to be higher or lower than the values that you did observe in those populations. So that's the overall framework. Okay. So how do you deal with that then? Well, one approach is to simply impute those potential outcomes, and typically people don't talk about it as imputing the missing potential outcomes, but that's essentially what you're doing. So if you just do an outcome regression, that is, you say fit a linear model with the outcome being months to recovery, you just jam those two things into one column, and then you get the beta, the coefficient of surgery on that outcome. Essentially what you're doing is imputing those missing values using a predictive model, and then taking the difference. So an alternative to doing that is covariate matching, which is that so for each question mark there, you find somebody in that population who's very similar to that person, but was in the opposite treatment group, and then you assume that what happened to that person is what would have happened to the original person. So that's a matching method, and that requires a definition of patient similarity. What does it mean for two patients to be similar to each other? And a big problem with doing that is that the more covariates you have, that is, the more ways of comparing two patients. Like, let's say somebody is 50 and female and of Vietnamese descent. Is that person more or less similar to somebody who's 50 and female and of Guatemalan descent, or to somebody who's 60 and female and Vietnamese descent? So how do you define that thing? And the more covariates you have, the harder and harder it is to find exact matches. So those are kind of one broad way of thinking about this, is as imputing those missing outcomes, either using a prediction model or by using covariate matching. Okay, so when does this fail? Sorry. This is okay. So this can fail if the regression model is not of the correct form. So of course, if you're imputing those potential outcomes and you're using a model and the model is not right, like you're not accounting for a particular covariate, or one of the covariates, you actually are missing an interaction, or it's a squared term and you put it in as linear, then the imputed value that you're going to get is not going to be close to the real value that you are missing. So that can happen, yeah, like I said, if you're not including all the variables that affect the, this should actually say the outcome, not the treatment assignment. And also, if the treatment spills over between patients, this is actually a general problem. Like if you have a vaccine study or something like that, where the outcome is a patient gets a disease, well, you have a herd immunity effect from the vaccine, that if one patient gets treatment, that actually decreases the likelihood that another patient will get the disease, because it stops the spread of the infectious disease. And so those cases where there's network effects are very hard to deal with in general. Okay, so but there's another approach besides trying to impute these missing values. What if we took a different approach altogether? So we know that RCTs work because when we randomize the treatment, we get on average populations that are the same in the treated and in the control cases. So what if we just look through our data and we find subgroups of patients in our study, because we know overall the two patient populations are different, But what if there are subgroups in our study where the treatment decision was as good as random among them? So then we have like a small RCT within our data set. If we have similar patients, they'll have similar treatment probabilities. So if we had just done covariate matching and we were just, as in the imputing case, where we just took a patient who's similar to this patient but in the opposite treatment group, if we're doing that, if those patients are the same, then they also have the same treatment probability. So this actually works for doing covariate matching, does work to find those mini-RCTs. But also, if the probability of treatment is constant for a group of patients, then the treated and control populations within the group are the same on average. So that's what I said before. So let's have a closer look at that. So here we have the orange and the teal patients are the treated and the untreated. So you see in the bottom margin, we have different populations. So there's more circles who got treated, and but in the untreated population, the control population, it's kind of an even split between the circles and the squares. That's if you look at it overall. But if you stratify by these buckets of the probability for having been treated, then you actually get populations within those buckets that are the same, at least in the ratios. So you have for that low probability treatment group. So the way that this looks is like if you're a square, you're less likely to have gotten the treatment, right? And so this top strata has more squares in it. And the ratio of circles to squares is the same in both groups. And this middle strata has like one square in it in each group, and the bottom one has no squares. So this is just like a little figure, but mathematically you can show the same thing, which is that if you stratify your sample by the probability of having gotten the treatment, of being assigned the treatment or not, then you'll get the same population within each of those stratas, or populations that are statistically the same, as good as random. Okay. Of course, the issue with doing that is that you don't actually know the probability of treatment for each patient. So what you have to do is you just estimate it using any kind of probabilistic classifier, and typically people use logistic regression. And so that logistic regression will give you a probability for each patient. And then the typical thing that people do is just stratify the data into the buckets of roughly equal treatment propensity. So you can choose 10 buckets, 5 buckets, whatever. And then within those buckets, since you have essentially an RCT, you can just ignore the missing potential outcomes, and you take the difference of those averages in the two columns. And then you just average over the results within each strata to get the population result overall. So there's also actually other things you can do with the propensity score. That thing that you estimate is the probability of treatment is referred to as a propensity score. But besides stratification, you can do a couple of other things. So one is matching. So you just shrink down each strata to 2 patients, 1 from each treatment arm, but the analysis is the same. I mean, stratification and matching you can really think of as being a continuum from stratification to smaller and smaller buckets to just 2 patients in each bucket. You can also do weighting, in which you take your original population and you upweight the patients that you need to be more representative of if you had randomized. So you see here in this figure, you have this one patient up at the top, this orange circle, and the top left has a very low propensity of having been treated, but did get treated. So if you had been if this had been a truly random sample, you would have expected to see 10 of that patient. But in the bias sample where that patient had a low propensity of receiving the treatment, you only saw 1 of them. So you just need to upweight that person so that they contribute 10 instead of 1. And same with the people at the bottom left. There's a lot of them, but if it had been a random sample, there would have been fewer of those kinds of people. So you just downweight them. So when you do matching, either covariate matching, which I described before, or propensity score matching, and like I said, covariate matching you can think of either being a way of imputing those missing potential outcomes, or as a way of finding mini-RCTs. Regardless of what kind of matching you're doing, sometimes you can discard unmatched patients from the data. You can say, you know what, this person really doesn't have anyone else who's comparable to them from the opposite group, and I'm just going to get rid of them. So what's the implication of doing that? Well, It does improve the comparability of the two groups, so that reduces the bias you're going to get in your answer. But the cost is that you reduce your power to detect an effect because you've gotten rid of some samples that potentially could have been useful. So that's more variance or lower power, or two ways to say the same thing. And the other effect is a little more subtle, which sometimes people don't think about, which is that you've changed the population that the answer applies to. So you need to think about maybe if the people who aren't being matched, which is almost always the case, are systematically different from the people who are being matched, then now your study results only apply to the population who got matched. And so you need to consider if that is really the same population or a subset. So that's kind of a subtle point. Okay. So like I said, the point of the propensity score is to balance the covariates of the treated and the untreated populations, because now you're getting into like this, you're trying to find a miniature RCT, right? And RCT works because the two populations are the same on average in the two groups. What does it mean for the population to be the same on average? That means that their distributions of their covariates, all their pre-treatment attributes, are about the same within the two groups. So here's an example of that. Like, let's say we have two pre-treatment covariates, which here in this little figure, this little toy figure, I'm calling X1 and X2. Like maybe this could be their age and how many drugs they're taking or something like that. And you can see with the blue and the orange are the two treatment groups. So on the left, maybe you have the populations who are being treated and not treated. You see there's some difference there between those two populations. They overlap, but there's some systematic difference. And on the right-hand side, you can see that they overlap pretty much spot on. So you really can't tell from which population the blue and the orange dots were sampled, because they're pretty much the same. So how do you check then if your propensity score has done a good job at getting you into that RCT world? So what you do is you take all the matched patients and you just compare. Ideally, what you would do is you compare these two multidimensional histograms of covariates after you do your matching or your stratifying or your weighting, whatever it is that you're doing with the propensity score. Now, that's actually kind of a hard thing to do because this is a little toy example where there's only two covariates. And so you can imagine making a scatter plot like this in like 20 dimensions or whatever. And it's just not really easy to look at or understand. So people use heuristics, which I will describe here. Oh. So the most common heuristic that people use is this thing called the absolute standardized difference in means. And it's just a summary metric of the plots that I was showing. So all you do is you take the mean of each covariate in the treatment and the control arms, and you look at the absolute difference. So what's the average age of the treated and the average age of the untreated, and how far apart is that difference? And a rule of thumb that people use, and to clarify, there is no mathematical or epistemological reason for this, but it is a rule of thumb that is used, which is that all covariates should have absolute standardized difference of means less than 0.1 for you to feel good about how even these two samples are. And so you can imagine, well, why not just try to optimize this balance in the first place? And people have done that. So there are some approaches to fitting the propensity score that attempt to directly optimize that balance and get two groups that are pretty much the same in terms of their covariates. The reason that's actually kind of tricky is because, like I said, this absolute standardized difference in means is just one way of measuring kind of the difference between those two multidimensional histograms. And there's no way to say that one is better than the other. But ASDM, this is a pretty common thing. Yeah, people recommend that you check. One thing that you should not do, which is a common error that I feel like I should note, is don't use hypothesis tests to check the balance. So some people will say, well, here's my age in the treated, my age in the untreated. Why don't I just do a t-test and see if those are statistically the same or different? Well, the problem is that you're doing that potentially with many different propensity score models or many different matched samples, and you're going to find the one that gives you the best balance or the highest p-value, not the lowest p-value. You want them to not be different. The problem with doing that is that will always favor throwing away more and more patients, because smaller samples will have less significant differences because it's more likely to just be random. So this is not really like a case where you actually want to do a kind of rigorous statistical testing. This is purely heuristic. You kind of just eyeball the ASDM, and that will tell you if you're good to go or not. Okay, so interesting question. A lot of people want to know, well, what variables do I include in the propensity score model? And one thing that I just realized right now that I didn't put on here, that for me it's like a, you know, if you're a fish, you don't see the water you swim in. But now I realize that I didn't put this, is that you do not ever include any variables that happen after treatment, because they cannot affect the choice of treatment. So even though they might help you predict the treatment, you don't want those things. You only want the variables that happen before treatment that could have influenced the decision to treat or not to treat. So there's that. So now, among those variables that you have that you have available to you that exist before the treatment happened, which ones should you include and which ones should you not include? Well, if you have some variables that you decide not to include, they won't be balanced after matching the propensity score, because the propensity score doesn't know anything about them. So it won't be able to properly account for the difference in those variables if you don't include them in the propensity score model. So that will increase bias if those variables really are important confounders. That is, they are things that affect both the treatment assignment and the outcome. However, interestingly, sometimes if you balance an observed covariate, you can unbalance an unobserved covariate. So you can imagine there's a variable that you're observing that is important for the treatment assignment. It does affect what treatment you get, but it doesn't really affect the outcome at all. So it's not actually important to adjust for. But there's another variable that is negatively correlated with that variable, which does affect the outcome and affects the treatment assignment, but you don't observe it. Then if you try to balance the observed covariate, you can unbalance the unobserved covariate and actually increase your bias, which is kind of concerning. And the typical advice is include all the variables you can in your propensity score model. I still think that's a good idea, especially if you're working in the EHR world where you have tons and tons of variables. You kind of just hope that you will have enough variables and correlates for unobserved confounders that you won't have this. But there's no panacea, and so you really have to think carefully about the relationship between your observed variables and the outcome and treatment, and think about what is it that I might not be observing in this study, and is there anything that I am observing that if I were to correct for, that somehow would unbalance things that I'm not observing. And there's no mathematical way to test for that or know that, like that has to come from your domain knowledge. So when do these methods fail? Well, of course, if the propensity model is not of the correct form, that is, you assume that the probability of treatment depends on the some linear form of these covariates that you're measuring, but really there's a quadratic in there or some nonlinearity or whatever. Well, then you're not going to get a good estimate of the propensity score, and you're not guaranteed to have this work. Of course, if you don't include all the variables that affect the treatment assignment, like I said, if you have any unobserved confounders, you're no guarantees. If you have some patient groups that have absolutely zero probability of being treated or not treated, you have no guarantees. That is, the treatment is deterministic, so there's no way to possibly match those people with people in the other group, because there's no way they could have possibly gotten the other treatment. And again, like I said before, treatment spills over between patients. If you have network effects, everything is very difficult. Although there are methods to deal with that, but it's much more advanced. So something else you can do is actually combine propensity methods with outcome regression. So one easy way to do this is you do the stratification of the propensity score, and then you fit regression models within each propensity strata. Okay, that's fine. You can also just discard patients with extreme propensity scores, so then you get a kind of balanced subsample, and then do regression. You can do weighted regression with the propensity scores. So these are all kind of hand-wavy ways of combining outcome regression and propensity methods. The principled way of doing this is something called the augmented inverse probability of treatment weighted estimator, which is similar to what I've described above. It's just mathematically a particular way of doing that ensures that everything is efficient and it works. There's also these other methods that are more advanced called TMLE and DML. The key about all of these methods is that whether they ensure this rigorously or not rigorously, is that they provide this form of double robustness, which is that even if one of these models is wrong, that is your propensity model, it had a squared term that you didn't include, or the outcome model had a squared term that you didn't include, or an interaction that you didn't include. As long as one of those models is right, then you will be good to go. Just one of them has to be right instead of both of them being right. Of course, in reality, neither of your models is ever right. So this isn't really something you should rely on. But there also is some evidence that that suggests that if one of the two models is more right or closer, then that also gives you less bias. And so typically, these methods are the way to go. So let's summarize all of that. I like to think about two approaches to causal inference in the kind of point treatment setting, and one of which is where you impute the missing potential outcomes, and the other in which you just recreate randomized clinical trials, or you find mini randomized trials within the data, and so you don't need to impute, you can just ignore those missing values. And then there's also methods where you do both. So for imputing, there's outcome regression. For the Mini-RCT, all the propensity score methods are essentially trying to find Mini-RCTs. And you can do both, like propensity methods plus regression, or covariate matching. You can also think of doing both of these at the same time. But as I said before, covariate matching is really hard to do in practice. So when it comes to choosing an approach, there's a couple things you have to think about. If you're going to do an imputation-based approach, a regression approach, essentially, you should know, do you trust the outcome model? The regression that you're doing, do you think that is actually an accurate way that, like, under the hood of the universe, is your model how the universe is determining what happens to this patient? And if you're doing the RCT, Mini-RCT based approach, propensity approaches, you have to ask, do you trust the propensity model? Do you think that you're accurately modeling how the treatment is assigned to these different patients? And when you're doing, in both of these cases, you need to think about, do you have all the variables you need? If you're missing an important unobserved confounder, you're going to be hosed no matter what you do. And if you're doing matching and you're discarding patients, you need to think about, did I change the question subtly? Did I change the population in a significant way that I kind of need to update my table one, so to speak? So overall, I hope you don't think that all of that paints too grim of a picture, but no method is a panacea, and nothing you do can possibly control for unobserved confounding. There are a lot of these papers, if you read the literature, and there's a lot of theoretical guarantees, but the way to think about that is that the guarantee only guarantees that the answer is right in the statistical world, not in the real world. So that in the statistical world, you assume that you measured everything that you could measure, and that the model includes all the terms that you needed to include. In the real world, that's never the case. So take those things with a grain of salt. Another overall point that I hope you come away with is that combining propensity scores with an outcome regression is typically a good bet. So even if one of those things is wrong, you can protect yourself by doing them both at the same time. And the last point, which ties into the first point, is that since everything seems so grim, that these theoretical guarantees aren't really guarantees, and you can't really do anything about unobserved confounding, the best thing you can do is use your domain knowledge. That is absolutely the best tool to help you pick an overall approach, variables and models, because you are the person who, as an expert, knows, is it more valid, right, with these data to model? Do I have a better model of the treatment assignment, or do I think I'll have a better model of the outcome? And do I think I'm missing an important variable here or not? What do I anticipate the bias being? And so your domain knowledge is by far the most important tool. And I think with that, I'm going to turn it back over to Vinny.
Great, thanks, Alejandro. So let's see here. Great. So to take you back to our problem, actually, I want to reframe it in the terms that Alejandro used, because the propensity score approach we use here is a little bit unusual compared to the standard, which is to assess the benefit of a specific treatment, for example, within observational data. So as Alejandro said, to say, is this surgery versus this surgery, or surgery at this time beneficial compared to another approach? in our issue, we were trying to understand, well, what's the impact of an acute organ dysfunction here based on these SOFA score groupings and gradations on long-term outcomes. Obviously, that's not something we could do a randomized study for. We can randomly assign patients to more or less severe renal failure. And the reason we, again, needed to do propensity score was because of the lack of the ability to randomize, but also we needed to account for the likelihood that this specific patient would develop that acute organ dysfunction because, as I described before, different pre-existing comorbidities contribute differently to the likelihood that each patient experiences that organ dysfunction. So a little bit of a twist on how propensity score model is normally used, but I hope it kind of lends some insight into why we chose this method as a rigorous approach, our best approach to try to answer this question. So just to kind of take us through, some of the findings in the study, and here you can look at this paper that was published in 2018 in Critical Care Medicine. First, we looked at, well, how was the SOFA score reliable across our sepsis population? And here we see SOFA score on the x-axis ranging from 0. It theoretically goes up to 24, but we only had scores that go up to 21. The gray bars are the number of patients who had that score. So you can see it's more lower severity patients than very high severity. But as you got into those high severity groupings, mortality here in the black bars increased tremendously. So we had confidence that we were evaluating an appropriate measure of severity of illness in these patients. This is a graph that shows the fact that patients in sepsis often have coexisting organ dysfunctions. And so here, if we look at the 6 organ dysfunctions here at the bottom, and then the dots show you which of the organ dysfunctions they had. So for this first bar on the top axis, those are patients who just had isolated cardiovascular dysfunction. The next is those who had cardiovascular plus nervous system. The next, cardiovascular, nervous system, and renal. And this gives you a sense at a quick glance that patients with sepsis, which we all know, present with all these different kinds of organ dysfunction. And in fact, in our statistical analysis, we needed to control for this fact that nobody, we were trying to isolate the effect of any specific organ dysfunction based on the pre-existing likelihood that that patient would have developed that organ dysfunction, and also based on the concurrent organ dysfunctions which were happening in the hospitalization. And if that seems really complex, please read the paper, and hopefully we describe it in a more clear way there. So what did we do? We looked at hundreds of variables prior to the acute organ dysfunction from the year prior to sepsis. And what we did was we used a tree-based method called gradient boosting machines. And we set up a propensity score in order to say what the likelihood of any patient to develop cardiovascular dysfunction, coagulopathy, liver dysfunction. And here, what we show are among those, all of those pre-sepsis factors, which of them most increase the likelihood that the patient will go on to experience that dysfunction. And what we found was actually really consistent with what we see clinically. So in renal disease, the most important factors were a history of chronic kidney disease, ESRD, hypertensive kidney disease, etc. All of these things essentially are kidney disease comorbidities that greatly increase your chance of actually having AKI. What was interesting was when you look at nervous system, so this is a GCS measurement, age was number 1, but other persistent mental disorders, Alzheimer's, dementia, other dementia, history of altered level of consciousness, late effects of a stroke, paralysis agitans. So you can see here that it's kind of extracting with this machine learning-based propensity score, factors which are increasing the likelihood of developing that organ dysfunction. And then finally, I'll just point out coagulopathy, thrombocytopenia as a history, use of anticoagulation, liver cirrhosis, atrial fibrillation, etc. All of these factors contributed. And when we were able to look at these variable importance plots, we felt pretty confident that our propensity score was, in fact, helping us to assign the likelihood that the patients would develop acute organ dysfunction. I'm not going to go up into this too much, except to say that this was a way for us to look at distributing patients across the SOFA score within each organ subscore between 0 and 4 and look at the distribution of the propensity scores. And what we see here, for example, in renal disease, the propensity score was quite low here in the pinkish color for those patients who did not have any evidence of renal disease and acute organ dysfunction. And then, for example, those who had the worst degrees of acute injury, a kidney injury, also our propensity model differentiated them. And so you can see for some of these organ subscores, we're getting better separation, and for some of them, the separation is a little bit more challenging, for example, here in respiratory failure. Well, ultimately, what we did was we used this propensity model and we looked at long-term outcomes, and here are the results. Essentially, we found that uniformly, nervous system dysfunction, evidence of obtundation, confusion, motor system problems, delirium, etc., during the acute organ dysfunction were the most robust in terms of impacting long-term mortality. There was perhaps a signal here for liver failure, but what was really interesting was some of the ones that we think of traditionally as really increasing a patient's risk, like respiratory failure or cardiac failure, were actually not associated with a worsened long-term mortality, and if anything, maybe a signal towards quote-unquote benefit. I think it's difficult to interpret exactly what that means, but I want to emphasize we did a study of survivors, meaning those patients who had to live through their hospitalization. And when we looked at what were the most important factors for contributing to death in the hospitalization, indeed, respiratory and cardiac failure were very strong predictors of death. And I think this suggests that, if you survive your septic episode with organ dysfunction, you're healthy enough, you have a robust cardiovascular respiratory system, you're actually relatively a healthy person. Now here, I show that there's multiple squares and triangles and diamonds. And that's just to say, as Alejandro described, you can use matching, you can use other types of weighting, and you can also do this doubly robust method. We tried all of them because we weren't entirely sure which one to trust the most. But here you can see that the signals are relatively consistent across the different approaches. Okay, and we ended up summarizing that in our large community-based cohort of sepsis patients, we found that acute neurologic dysfunction during sepsis most strongly increased the long-term risk of mortality, whereas other types of organ dysfunction had a relatively modest impact on long-term outcomes. And if you have other questions or want to look at this study in more depth, please feel free to follow that reference. Okay, I'm going to end here, in the next couple minutes, just talking about some of the other work. I mean, can we trust propensity scores given, all of the challenges in how we design them and understanding, are we matching correctly? Do we have the right cohort? Do we have the right covariates to actually calculate the propensity score? And how do they compare ultimately to RCTs? And so I'll highlight this study, which was published in Critical Care Medicine in 2015, and in which they actually looked at propensity score analyses compared to RCTs in some specific domains. And here they outline RCTs, which included at least 200 subjects, compared to the results from a corresponding propensity score study, activated protein C in sepsis, low-dose steroids. And what you can see here is that in many cases, the results of the propensity score study and of the RCT study were similar, both on the same side of this relative risk threshold of 1, and in some cases, very close effect estimates. But in some cases, they were actually quite different. And I think this is the challenge of knowing how much confidence we can derive from a propensity score-based study is, sometimes, the effects may indeed be quite close, and other times it may not. And without actually doing the actual interventional study, we're still left with a big question about whether we can confidently act on those results. This is another way of displaying that. Where we compare the relative risk from the observational propensity score study against the relative risk of the RCTs, and things which fall along this line suggest that the effects are similar. You see that many of them do, but again, we have some notable outliers, which make us concerned about, the confidence that we should have in using these approaches. But again, in the face of a massive amount of observational data and the ability to use greater and greater richer and larger data sets from the EHR, hopefully we can employ these methods to make more and more targeted quote-unquote mini-RCTs. I want to point out a couple other references which were recently published, which I think if you're interested in diving into more depth, particularly in critical care, you should take a look at them. Daniel Leisman published this perspective, which was 10 Pearls and Pitfalls of Propensity Scores in Critical Care Research, a guide for clinicians in research. It's really well written, and it highlights some of these key points, which, Alejandro has already talked about. Propensity scores are neither more or less reliable than traditional covariate adjustments. They don't mitigate unobserved biases. They can be, in specific circumstances, extremely useful. And there's other points about how you should direct your attention to the underlying methodology of a propensity score. And then I'll also highlight this recent editorial, which is from David Maslov, who's the editor for data science for critical care medicine, as well as Dan Leisman, which is guidance about causal inference. So not just propensity scores, but other techniques. And as they point out in this perspective piece, we're seeing a massive increase in the number of observational studies, whereas just a slight increase in the number of RCTs. This article actually references another article, which is a publication from the editors across many pulmonary critical care and sleep journals about standards for observational causal inference arising from observational data. And I would highly recommend, if that's an area of research that you're engaged in or you want to be engaged in, take a look at that, because I think it'll give you a lot of pointers about, from experts in the field about the right approaches to take right from the start. So I'll summarize. RCTs are unique in their ability to establish causality. A variety of techniques are used to estimate causal inference within observational data. Propensity score methods are pretty standard by now, and in some cases can demonstrate consistent results with RCTs. However, as Alejandro stressed, clinical and methodologic expertise are essential to building these models and correctly, and ultimately results need to be validated in RCTs or other types of prospective studies to definitively establish highest quality evidence. I think we'll stop here and open it up for questions. Thank you.
All right, thank you very much, Drs. Liu and Schuler. We have a couple of questions already in the question box. The first question was, is it possible to get a list of the references that are cited in the presentation? And the answer is yes, absolutely. The webcast will actually be available within 5 business days on the SCCM YouTube channel. So you'll be able to access the presentation and all the citations there. If you have any specific questions, you can contact SCCM at support@sccm.org.
I also want to note really quickly about the citations, at least in the kind of methodological portion is that I did make a solid effort to make sure that all those are fairly didactic and accessible references. So I do really recommend looking into those.
All right, and the next question. Can you use bivariate analyses to pare down the number of covariates to use in your propensity score model?
That is a great question. The answer is yes, you can. Should you is a different question. Well, and I'll illustrate that in this way. I mean, imagine there's a variable that somewhat impacts the treatment assignment, but greatly impacts the outcome. Then that's actually a variable you do want to adjust for in the propensity score model, because even though it impacts the treatment assignment only slightly, that effect and that difference of propensity will be a thing that you want to adjust for in the final analysis. And so, but if you were doing a bivariate test to establish the relationship of that variable with the propensity score, with the treatment assignment, it might not come up as highly significant, and you may omit it. And so, actually, some people suggest including only variables that or targeting the propensity score mostly to variables that you know are associated with the outcome, highly associated with the outcome. And in fact, if you have a variable that is only associated with the treatment assignment, but not at all associated with the outcome, like it's just random, then including that variable in the propensity score model actually may decrease your well, it doesn't bias the analysis, but it increases the variance of the analysis. You'll have a wider confidence interval than you would have otherwise, and then if you had just omitted that variable, even though it's a variable that is highly associated, and you would want to include it if you were doing these like univariate analyses. So hopefully that answers the question.
All right, and the next question. Can you speak to sample size for propensity score methodology? And are any of the approaches possible for smaller sample sizes?
So there's no substitute for more data, although the bigger is not always better. So if you have a larger data set with more bias, and that's exactly what these observational data sets often are, you may have thousands of patients, but their treatment was assigned to them in a highly biased, non-random way. That might be worse than a very small data set with random treatment assignment, like you often see in these 30, 40-person RCTs. There's not really a solid way to answer that question. The answer is always that it depends in terms of sample size. If you're looking for an effect that you think is going to be really big, you think the effect of this treatment on the outcome is substantial, then you don't need that many patients in your study to determine that, to see the effect of that intervention. If you're looking at an intervention that you think is going to have a very subtle effect, then you're going to need a lot of patients in order to uncover that, and that applies whether or not you're using propensity score analyses. So that's pretty much the answer to that question. Is it depends, and there's no particular method that's better for small data sets, or all methods benefit from more data.
Okay, we have one more question at this point, and one of our audience members, he's published a few retrospective propensity match studies, and he's actually gotten pushback from reviewers who seem to not know exactly what propensity matching is. And so the question is, do you guys have any suggestions on how to succinctly explain propensity score matching?
Wow, that's a tough one. I would say request a new editor. No, I'm kidding. I think that propensity score methods are actually widely used now, and I think that editorial staff at most high-profile journals should have folks that are experienced in actually refereeing articles that use those methods. In that case, I don't have any really great recommendations except to say looking for some very high impact publications within using propensity score in observational data at large, not just in critical care, but kind of in that get published in the highest profile journals will help solidify the case that this is a well-worn methodology. And I think citing some of the resources that I mentioned at the end, which are from editorial staff, from all of the pulmonary critical care journals, endorsing certain approaches to these methods will actually be helpful as well.
I want to add one more thing there, which is that I have seen reviews I have seen papers where the claim is, oh, we use propensity scores, so we're good to go. End of discussion. Here's the results. Here's the discussion. Done. I think it really strengthens your study if you take the time to explain also the kind of what the pitfalls and say we use propensity scores. This is not a guarantee of the answer being correct, but given our domain expertise, we believe that these are the important confounders, and here's why they're important. These are the unobserved confounders we may have, and here's what their effects might have been if we had them. And just be honest in that discussion. I think that can help as well with some reviewers who will just kind of out of hand reject something because they think you're being too blasé or something like that.
All right. Well, I think that concludes our Q&A. Thank you again to our presenters and also the audience for attending. Again, you'll receive a follow-up email with a link to complete an evaluation. The link to that evaluation is also listed in the chat box for your convenience at the bottom of this page if you do not wish to wait for the follow-up email. You only need to complete it once. There's no CME associated with this educational program. However, your opinions and feedback are important to us as we plan to develop future educational offerings. Please take 5 to 10 minutes to complete the evaluation. The recording for this webcast will be available on the SCCM YouTube channel within 5 business days. And that concludes our presentation today. Thank you all for joining.